In this example of using the half reaction technique for balancing redox reactions, we're going to consider a situation where we have a basic solution environment. So first of all, let's look at the reaction that we're supposed to balance, the equation we're supposed to balance. Again, emphasizing this time we're considering a basic solution condition. There are a lot of similarities in the approach used in basic solutions as in acidic solutions. The first of which, of course, is we have to go through and assign oxidation numbers to all of the species and identify what is being oxidized and what is being reduced. And here you can see that the phosphorus went from +1 to +3, so it was oxidized, and the antimony went from +3 to 0, so it was reduced. So as we did with our acidic solution condition, we're going to separate out the oxidation half reaction and the reduction half reaction. Now remember, the approach is very similar, so the beginning of this is going to parallel what you've seen in other examples. Let's take care of our oxidation reaction first, atomically. And to do that, I can see that I don't have enough oxygens on the left side. I need 3 oxygens on both sides, and as before, when I need more oxygens, I add in water. So I added in an extra water molecule on the left side, and then I go ahead and I take care of the hydrogens, and I don't have enough hydrogens on the right side. I had 4 on the left side. I needed 3 more. That's why I added in the 3 hydrogens. So right now, at this point, that half reaction is taken care of atomically. So now let's take a look at the reduction half reaction and do the same thing. I don't have enough oxygens on the right side. I need 2, so I take care of that by adding 2 water molecules, which of course then changes the hydrogens. So I need 4 hydrogens on the left side, and as we've previously done, we take care of those by adding in 4 hydrogen ions on the left side. Our next step, of course, is to take care of things charge-wise, electronically, and so I go to my oxidation half reaction, and I can see that on the left-hand side, I've got a total of a -1 charge, and on the right side, I can see that I actually have a +1, so I got to bring that down 2. That's why I added in 2 electrons. So that's now electronically balanced. And now I do the same thing for the reduction half reaction. The right side of my equation was neutral. On the left side, I had a +3. I got to bring that down to 0. So I got to cancel out 3 positive charges with 3 electrons. So again, you can see very much like what we did in our acidic solution problem. Now, as previously in many examples, we now have to have the number of electrons be equivalent, and we can see that the common multiple between 2 and 3 is 6. So to get 6 electrons in my oxidation half reaction, I multiplied everything by 3. And to take care of everything in my reduction half reaction to get to 6 electrons, everything was multiplied by 2. So up to this point, we've done exactly what we did in our acidic solution conditions, and we'll continue in that vein. So next, we're going to take those 2 equations, those 2 half reactions, and we're going to combine them. We're going to add them up. So here are the 2 that we just came up with, balanced atomically, electronically, and the actual number of electrons being exchanged. We're going to add them. So as always, everything on the left-hand side of both equations come down, everything on the right side come down. So here's my summation of those 2 half reactions. And you start to see pretty readily there are going to be things that we can cancel out. So the first thing I noticed is I can cancel out waters. I've got 3 on the left side, 4 on the right side, so I have no more waters on the left side. I have 1 left on the right side. Next, I noticed the hydrogens were appearing on both sides. So all 8 of them on the left side disappeared, 8 of the 9 disappeared on the right side, but I still have 1 left on the right side. And then, of course, the electrons, the 6 that were being added or released, are eliminated. So now I'm going to rewrite the equation one more time and write down all those species that survived, so to speak. Now you'll notice here is where the difference just occurred. You noticed when I canceled everything out, I still had a hydrogen ion on the right side, which would indicate an acidic condition. But we were given the premise at the beginning that this had to be basic. So we know from our work with acids and bases, the way you cancel out hydrogen ions is by providing hydroxide ions. So I needed to neutralize 1 hydrogen on the right side. So you see I've put an extra hydroxide on the right side. And whatever I do to the right side, I have to do to the left side. So you can see there's a hydroxide appearing on the left side of my equation also. So now when we consolidate things, we know that when hydrogens and hydroxides encounter each other, they'll form a water molecule. So consolidating things, on the left side, everything is as already written, but on the right side, when I consolidate the hydrogens and the hydroxides, I ended up with a total of 2 water molecules on the right side. So now you can see it is balanced atomically, electronically, electron-wise, and you can see now it is indeed a basic solution. So these are done very, very similar to the acidic condition ones. It's just at the very end, you have to make it alkaline by adding hydroxides in.